In the next videos, we will discuss about modeling with continuous time Markov chains. In this video, we introduce a few basic concepts about them. We discussed in the previous videos discrete probabilistic systems. In other words, models whose behavior is dictated by probabilities and where the system evolves in steps. In each step, the model will get its variables updated and thus its state updated. The updates are done in steps, and we can talk about the behavior at step 1, 2, 3, and so on. The relation between step number n and the real notion of time is left unspecified. The key difference in the case of continuous time Markov chains is that the time of the model is treated carefully to connect it explicitly to the real time. To do this, the model stays in the current time for some period of time, and then it changes its state. The amount of time it waits in the current state is carefully calculated so the model time corresponds to real time. We will look into some details how this is done. Models standing for fast behavior will stay less time in the current state and thus update their states more often. On the contrary, models for slower behavior will stay more time in the current state and thus update their states less often. In one sentence, CTMCs offer a more careful modeling of time and its influence on the pace of state change. Here is a definition of continuous time Markov chains, or in short, CTMCs. Intuitively, they are such probabilistic systems whose future evolution can be fully described based on its present state. We don't need to consider a long trace of the past behavior to reason about its future behavior. Only the current state is needed. Obviously, its current state was influenced by its past, and the future behavior is determined by its present. Formally, we say that the probability that at some point s plus t the system is in state x s plus t, given that now at time s is in state xs, and given its whole set of past values before time s, is the same as the probability at point s plus t the system is in state x s plus t, given only the information that now at time s the system is in state xs. Let's think now about the states of a CTMC. The system starts from one of the states, and then, as time advances, it will jump from a state to another, wait for a while, then jump again, and so on. Each of these jumps is obviously probabilistic, and several options always exist, depending on the current state and, potentially, on the current time. In other words, the behavior of the system may even change in time, and we could see very different phenomena as the time advances. To keep matters simple, we only consider in this course the simplest version of such models, where the probabilistic jump from a state to another is only determined by the current state, not by the time. These are complex enough models, and in many practical situations they are enough to write a realistic enough model. Such models are called time homogeneous, and the formal definition is on the slide. It expresses the intuition in mathematical terms. The probability of going from state I to state j is the same no matter what the time is when we are in state I. So for such systems, we can denote by Pij the probability that the system is currently in state I, and its next jump will be to state j. You may remember from the previous videos that these probabilities now determine a discrete time Markov chain. So if we have a time homogeneous continuous time Markov chain and we only consider the probabilistic jumps between the states, we get a discrete time Markov chain. This shouldn't be surprising. Essentially, if we don't consider the careful notion of time and only take the step-by-step probabilistic jumps, then we will of course get a discrete time version of the same Markov chain. Consider the example of a system where we have a number of elements, some birth processes and some death processes. So we define the state I of the system to be that where we have exactly I elements in the system. Following a birth, we get one more. In other words, we move to state I plus 1. Following a death, we will have one less. In other words, we move to state I minus 1. To think about the probabilistic behavior of the system, we need to reason about the two possibilities we have in state I, that of a new birth or a new death happening next, modifying the state of the system accordingly. Intuitively, we can think that we have two clocks in state I. The one that rings first will determine the next state, depending on whether it was the birth clock or the death clock. The time when it rings determines the time of the next jump. We have to make all of these more formal so we can see how simulations and analysis can be done for such systems. Let's take some simple math to look at it. Let's focus on the waiting time in the current state of a CTMC. This is a variable x that takes non-negative values. Remember that in CTMCs only the present counts and we don't need the past to determine its future. For the waiting time, this means that if we already have been waiting for t units of time and we ask what's the probability that we will wait s more units of time, this is the same as asking whether we will wait s units of time when we have just now arrived in the state. Mathematically, we write that the probability of x being larger than t plus s, knowing already that x is larger than t, is equal to the probability of x being larger than s. Such variables are said to have memoryless probability distributions. There is an old result characterizing such variables. I don't get into the details of proving this result and I only formulate it here. It says that any such variable is exponentially distributed. So this means that we know how to sample such variables. In computational terms, it means that we know how to simulate the probabilistic waiting time in each variable. The simulation will of course depend on a parameter that's a function of the current state, meaning that in different states, the waiting times will obviously be different. We will get later into the question of how to calculate exactly this parameter. Just a side note, a similar result also holds for discrete probability distributions. For those of you who are more mathematically inclined, here is a detailed proof with all mathematical details that the holding or waiting time in any state of a time homogeneous CTMC is exponentially distributed. It's essentially the same argument that I explained intuitively already, and I will not go through these details. I just show them here so you can return to this slide if needed. In the next video, we will discuss the probabilistic approach to biomodeling, culminating into Gillespie's exact stochastic simulation algorithm, which is the cornerstone of all stochastic model analysis. To prepare for it, I only introduce in this video one more concept, that of the grand probability function. The way to reason about the dynamical behavior of a continuous time Markov chain is through the grand probability function. For a system with species or variables S1, S2 and so on up to Sn, this is a function that expresses the probability that at time t we have x1 of the first species, x2 of the second, and so on. It's a big deal to know the grand probability function because through it we may get a lot of useful information, such as the expected amount of molecules of species S1 at time t, or the standard deviation for the amount of molecules of species S1 at time t. In the next video, we will discuss how to calculate or describe the grand probability function.